This lecture is going to cover nonlinear regression as a way to get us towards neural networks and more advanced machine learning methods. So neural networks and most machine learning methods have something called a cost function that has to get minimized. And a large part of advanced machine learning is training these cost functions. And I think the best way to get an introduction to this is by covering this topic of nonlinear regression, which also happens to be, I think, a very useful tool for IMC students. I think there are many applications of this. All right, so what is nonlinear regression and how is it different from linear regression? Well, first off, linear regression we've studied in many previous classes allows us to estimate models that are said to be linear in the parameters. Okay, so that doesn't mean that they have to be linear functions, they just have to be linear in the parameters. So the example that is very familiar is multiple linear regression, where you have some sort of hyperplane that is linear. But in previous courses, we've discussed how maybe the relationships are nonlinear, but we can make some sort of transformation to address that. So, for example, by adding a log transform to y, we could deal with heteroscedasticity by transforming x with a log function that introduced diminishing returns. Okay, so this is still a function that is linear in the parameters. So what makes it linear in the parameters is that I have some dependent variable that is a linear transformation of some set of predictor variables. So what do I mean by a linear transformation? What I mean is that all of my predictor variables are just multiplied by some constant and they're added together. There's nothing more complicated than multiplying my predictors by a constant and adding them up. Here's another example where some of the variables turned out to be interactions. That's okay as long as we know about that ahead of time, because what I have here is just a linear transformation of a bunch of predictor variables. Okay, so what is nonlinear regression? Nonlinear regression involves some sort of nonlinear combination. So I can't write it as the parameter times some predictor added up. So here is one example, the logistic model, which is going to actually turn out to be a neural network, very simple neural network. All right, so this is a topic that gets covered in a lot of regression textbooks. One of the classics is the book by Netter, Wasserman, Kuttner. There's various versions of this book with different first authors. So Kuttner, I've taken one of his exercises just to discuss with us. So we're to indicate whether these things are intrinsically linear. So intrinsically linear meaning we can introduce some sort of transformation to make it linear, or if they're fundamentally nonlinear. Okay, so this first function is intrinsically linear because if I were to log both sides, I have the log of f, and then what happens on the right is the log of the exponent cancels out, if you will, and we're just left with beta naught plus beta 1 times x. So this first function is intrinsically linear because the log of this function is just beta naught plus some parameter times an x. On the other hand, these next two functions are not intrinsically linear. They are nonlinear functions because I can't take some sort of simple transformation and make it this sum of a parameter times predictor variables. All right, so there are many nonlinear functions in this world. We've actually seen some examples of these nonlinear functions already, but we didn't really go into a lot of depth on how you estimate them. So when we talked about matrix factorization, recommender systems, that's fundamentally a nonlinear function. Logistic regression is a nonlinear function. neural networks are going to be this as well. But here's some specific examples that I think are very useful to talk about. One is the logistic model. So the logistic model is important to know about when we get to neural networks. With neural networks, we're going to need to have something called a squashing function. So a squashing function is where we're going to have a bunch of inputs that can be very big or very small, but we want to squash it to be within a certain range. Okay, so we can think about the inputs to a node are going to combine to form some x variable that can either be very high going off to infinity or very low off to negative infinity. And this squashing function is simply going to take the sum of the inputs and squash it to be between, say, 0 and 1 or 1 and minus 1, whatever we choose to be. All right. So this logistic function has this functional form, and we can think about what are the properties of this function. And so one way to think about this is if I were to let x be 0, okay, if x were equal to 0, then e to the 0 is equal to 1. And so I end up with beta naught divided by 1 plus beta 1. And so that is going to be the intercept. That's where this thing crosses the y-axis. So when x is equal to 0, that's where it crosses. Now, if this denominator, so let's say beta 2 is positive for a second. If beta 2 is positive and x goes off to infinity, then what happens is I have a positive number times a very big number, and then I exponentiate it. It gets very, very big. All right, so what's going to happen there is this whole denominator is going to go to infinity, and this whole function will go to 0. All right, so as this thing goes to infinity, the denominator gets extremely big, and the whole function goes to 0. So it's like this sine curve. As x gets bigger and bigger, this thing is going to approach 0, and it's going to approach there pretty quickly, because anytime you exponentiate something, things get very big. Alternatively, okay, so let's just keep beta 2 positive for now. As x goes to negative infinity, this term goes to, it's going to get smaller and smaller and smaller. And so this whole thing is going to vanish, and you're just left with beta 1. All right, so that's why the asymptotes here are at 0 as x goes to positive infinity, and beta naught as it goes to negative infinity. Now, if we were to flip the sign on beta 2, then of course everything changes, and we would go to beta naught as x goes to positive infinity, and we would go to 0 otherwise. All right, so that's one nonlinear function. Let's talk about another one. This other function I find to be one of the most useful functions around. Short of linear functions, which of course are extremely useful. This one I tend to use quite a bit. It's called the learning curve. So the reason it's called the learning curve is that it's often used to describe how someone learns something. So let's just think about typing. Okay, so if you had never typed before and I gave you a typing lesson, this is like the number of hours you've spent practicing, and this would be your typing speed. So what happens when you learn something is often you make initial very rapid progress, where your typing speed increases from very low to you make good progress pretty quickly, but at some point it flattens out, because you can't type in infinitely fast. It's going to approach some sort of an asymptote. Okay, so this learning curve function captures this notion where it kind of increases quickly and then it approaches an asymptote. So here's the exact function. So let's just kind of think about what happens. All right, so as x gets really, really big, what happens is we have negative beta 1. So beta 1 is a positive number, so this whole term is going to go to 0. So if that goes to 0, beta 2 times 0 means that this whole second term vanishes, it goes away. So as x gets bigger and bigger, this thing gets smaller and smaller, and the curve approaches beta naught. So beta naught is the asymptote. So it's the value that we approach as we get bigger and bigger. So it's like the fastest that you could possibly type. So whatever the world's record is for typing speed, that's what what this beta naught is. All right, well, let's think about another situation where I let this x be 0. Okay, so that would be the y-intercept. And so if you think about what happens when you make this 0, well, you get e to the 0, which is 1. And so the resulting function, the y-intercept, evaluated at 0 is beta naught plus beta 2. Okay, so what that really means is this beta 2 is telling us the distance between the asymptote and the intercept. All right, cool. What does this beta 1 do? Well, beta 1, you could say is the steepness or the learning rate. How fast does this thing learn? As beta 1 gets bigger, you get a curve that approaches the asymptote more quickly. As beta 1 gets smaller, it approaches it less quick. So I've actually shown this on the next slide, where you can see the black line. I have this learning rate of 1.1. The red line, you can see I've decreased it. So it's like the person learns more slowly, and so the red curve indicates slower learning. The green line, on the other hand, increases this beta 1, and so this person learns how to type faster, if you will. The blue line does something completely different. It flips it around, where you're going to see the intercept is now down at 19. So remember the beta naught is the asymptote. I may have said intercept a minute ago, I meant asymptote. The asymptote is 19, and then the y-intercept is going to be 30 higher than that. All right, so that's why it starts out here at 49 as 19 plus 30. The others all have an asymptote at 49, and they start out 30 units below. All right, so that's a very concise way to represent this learning curve. I want to give you an example of how I used this learning curve in a piece of research that I did. So we were asked to figure out what's the value of a customer review, what's the value of having customer reviews, which is kind of a big question. So the way we approached this was we identified some assumptions. So here are the assumptions we made. So first, every product that we carry has some inherent conversion rate without any reviews. Okay, so without any reviews, a certain fraction of people who see that product will buy it. Okay, so now just kind of jumping ahead, that's the y-intercept. So if on the x-axis we plot the number of reviews, so that's often called volume in the review literature. At some, if I have no reviews, I have some conversion rate. Assumption 2 is that each product has some upper bound on its conversion rate, probably less than 1. All right, so if I had an infinite number of reviews, what would be my conversion rate? And so then that would be this asymptote that I have. And then as reviews accumulate, presumably this conversion rate goes up. If all the reviews were bad, the conversion rate could decrease, all right? But that would be like this blue curve. So, this learning curve would allow for either possibility, where as reviews come in, my conversion rate goes up. If all the reviews happen to be bad for my product, then presumably I'd get one of these blue curves that decreases. All right, so then the value of reviews is simply the difference between what the conversion rate I have if I have no reviews and the conversion rate I have with an infinite number of reviews. All right, so that's it's shown as gamma 1 here. I changed my notation since, all right, that should be beta 1. But beta 1 is then the value of reviews. All right, so we actually estimated this with data where we had products and we could follow through their history from when they had no reviews to when they had many reviews. And you can see what happens to this conversion rate over time as we increase the number of reviews. You see the conversion rate goes up a bit. And we actually aggregated this. You could do this for a single product, or you could aggregate it across products in a particular category. So how important are reviews in electronics versus apparel and so forth. And so what you can see is that having reviews actually helps you. So let's just look overall for now, which is what I'm showing in this plot. Now, if you remember, this first parameter is the asymptote. So there's an asymptote at a conversion rate of 1.6%. So 1.6% of people who view your product end up converting it on this particular site. And you're going to remember that this gamma 2 describes, gamma 1 describes, let's go back to this, I got to make sure I got this right. Gamma 1 in this case is the difference between the asymptote and the intercept. So in this case, the conversion rate increases about 1%, so 0.0095 is about 1% from the point where you have no reviews to when you have an infinite number of reviews. Okay, so in other words, your conversion rate goes from about 0.006% up to 0.016%, which is a pretty substantial increase. Now, this other parameter determines how quickly the conversion rate goes up. And so what you can see from this graph is it really increases pretty quickly. By the time you get about 10 or 15 reviews, you're most of the way there. So going from 15 to 20 reviews doesn't help your conversion rate, but just even having 10 to 15 reviews helps the product a lot. All right, so that's an illustration of this. All right, well, how do we do this? Well, we're going to use nonlinear least squares to estimate these parameters. So in general, we have some function like the learning curve, and we've got some unknown parameters associated with this. So in the case of my learning curve, the unknown parameters were the asymptote, this place is going to identify the intercept, and then the how steep the curve is. All right, we're going to estimate these with least squares. So least squares is what we've been using for linear regression and many other methods. K-means basically is minimizing the least squares criterion as well, but probably the closest analogy would be linear regression. All right, more on how we do the estimation next. For now, I want to show you how we could do this in R, and I'm going to do this with a particular example. So in this example, we have a computer manufacturer who is testing different price points for a computer. So we have 10 different price points studied, and at each of these price points, we interviewed 100 heads of households and asked them whether they would buy the computer at the given price. All right, so we're told to plot y against x, and so if you go to the next slide, actually, I don't have those plotted. Let's go over to R for a second, and let's go do this here. I'm going to bring in the data set so all of you have the data on this R script on Canvas. So let's go plot the data. And so what you'll see is x1 is the price that I charge for the computer. This is the probability that they say, yes, I'm going to buy. And it's what you would expect. As the price increases, the probability of saying yes decreases. All right, good. Well, find the starting values for this algorithm, assuming that beta naught is equal to 0. So what's happening here is it's very important to start the search for the best parameters at a good place. What we're going to find is that if you start in a bad place with bad, initial values of beta, we probably won't end up with the optimal solution anymore. So it's very important to choose good starting values. And so one way to do this is to try to linearize this in some way. And so Kuttner recommends setting the value equal to 0. So why would this be reasonable? Well, if I charge you an infinite amount of money for a computer, how likely are you to buy it? And the answer is you're probably not very likely. So as x1 goes to infinity, it's not unreasonable to think that this function would go to 0. All right, and so that's when setting this to 0. Now, once you've set this to 0, it's pretty easier to linearize this. So if I take the log of both sides, I get the log of y is equal to the log of beta 2. And then if I take the log of a product, this becomes a sum. So plus negative beta 1 times x. All right, so if we go over to R, I'm going to estimate just a simple linear regression where I regress the log of y on x. And so now I have some good starting values. So how can I estimate this particular function in R? Well, the answer is there's a wonderful function called NLS for nonlinear least squares. All I have to do is provide the equation. So you'll see I've just typed in this equation exactly. Give it the data set name. So it looks a whole lot like our friend LM, the linear model. The only thing that's different is I have to provide starting values. So let's go look at my starting values. So I'm providing a starting value. This is just like, where do you want to start the search for the best parameters? We're going to start with beta naught equal to 1. Beta 1, remember, was just negative the slope from this. Okay, and then beta 2 is the exponent of the intercept that came out of this. And so that comes from, remember, I set this equal to 0 and took logs of both sides. All right, great. Well, let's go estimate this. And we have similar functions like summary as we do for LM. And we can see that R has estimated the parameters. So B naught is going to be this asymptote. We'd expect this thing to be 0. It's not 0, and it's actually significantly not 0. I think we're extrapolating, and that's why this is not 0. But then remember that beta 2 is going to be the y-intercept. So if we take beta naught plus beta 2, we get the y-intercept. So the y-intercept is going to be about 91% if I add 0.08 and 0.83. And if we look at our graph, that looks pretty reasonable. Beta 1 is the learning rate. Superimpose this on the plot is part D. So let's go do that. I'm going to go superimpose it. So the way I'll do this, I'm going to generate a bunch of x's. And then what I'm going to do is just use lines to superimpose it. And so you see a pretty good fit there. All right. So what I've tried to do here is show you how you can estimate this. There's some other parts that I emphasize when I teach this in a stats class, but I'm not going to emphasize it here. Part G is obtain 95% confidence intervals, and so we can do this very simply with confident. It's exactly like what you have with linear regression. Confident works with linear regression as well. All right, so you have my solution here, and that's a short introduction to nonlinear regression.